nice worksheet that describes Newton's three laws of motion. And this is great for your notes, and you should keep it. It describes it. It has all three of them. The first law, law of inertia. The second law, F equals ma. And law number three, the third law, the law of equal and opposite forces. It kind of describes in two ways. One, it gives a detailed kind of scientific definition at the top. And then at the bottom, it sort of gives a simple English, easy to remember definition, which I like a lot. And I think you should think about using that rather than the complicated definition. Okay, but we'll go through them and just take a look, okay? So the law of inertia, that's a great way to remember this, is the first law is the law of inertia. And basically it says something will stay at rest unless it's acted on by an unbalanced force. And it will stay in motion unless acted on by an unbalanced force. Or the simple way to say it down here is things will keep moving or stay at rest unless a net force acts upon them. Okay? The second law is the famous equation F equals ma. And that's a good way to remember it, with this equation. Okay? And it talks about the way to think about it mathematically, but the way I think about it is the bottom one, which is forces cause acceleration. Okay? Forces cause acceleration, but larger mass resists acceleration. Okay? So a nice way of saying it is forces cause acceleration, but large masses, resist being accelerated. They require more force. Okay? And then the third law, the law of equal and opposite forces. Well, whenever one object exerts a force on another object, the second exerts an equal and opposite force on the first. Okay? But a simpler way to say that, which I like a lot, is for every action force, there is an equal and opposite reaction force. And I think that's really handy. So if you don't know these, this is a great time to learn them. Okay, I have a couple problems down below I'm going to go through real quickly. I'm not going to spend a lot of time on these. First, I'm going to do this problem here. So I'm going to draw a picture of this first. I think that's always a good way to go. So I'm going to draw a free body diagram. And it says if a person pulls on a cart to the right, so he's pulling on the cart to the right with a force of 10 newtons. Okay, now I'm always going to draw a compass, right? And the right is going to be positive, and the left is going to be negative. Okay? And the second person pulls to the left with a force of 3 newtons. This is a really simple problem, really, right? This is a review for you. It says, well, what is the net force and the direction of the on the cart? So the net force is the sum of the forces, or the total force. So whenever you see the word net, you should think the sum of all the forces or the total of all the forces. So if you look at this, the 10 Newton force, you're going to add these together. You're going to sum them up. Well, the 10 Newton force is to the right. It's positive, so that's going to be 10. The 3 Newton force is to the left. It's going to be negative, so that's minus 3. You're going to add these up. 10 minus 3, 7 newtons. Now, since this is a positive number, okay, F net is 7 newtons. It has to be to the right because this is a positive number. Okay? Okay. Since there's a net force on this object, on this cart, then this object is not at equilibrium. Okay? It's not at equilibrium. There's a net force. Okay? And since there's a force acting on it to the right, a net force acting to the right, there is an acceleration. And that acceleration is in the same direction as the force. It's to the right. Okay? So when you see this, when you see a net force, you should say, hey, I've got a net force acting on this object, this cart. It is not in equilibrium. It's being accelerated to the right. Okay? And the same direction the net force is occurring. Okay? So let's go over here and say which of the Newton's 3 laws applies, law 1, 2, or 3, to this group of situations. Personally, I think a couple of these are sort of vague, and I'm not the biggest fan. So I'll go through and I'll kind of give you my take on this. Okay? Okay. When you put a book on a table and the table pushes on the book, so this is number 1 here, right? So you put a book on the table. There's the book, there's the table. Okay? There are two forces acting on this, right? There's a gravity force from the book downward, right? But there's an equal and opposite force acting on the book upward, which is the normal force, okay? Which is equal and opposite to the gravity force, okay? And that's holding the book on the table, okay? So the answer to this one, I think the best answer anyway, is 3, okay? When you put a book on the table pushes on the book, okay? For every action, there's an equal opposite reaction. Whenever one object exerts a force on the other object, the book on the table will exert an equal and opposite force on the book. Okay, that's law 3. Number 2, a person is pushed forward into their seatbelt when a car stops. Well, you're in a car, right? And you have a seatbelt on. The car stops suddenly. Okay, you're a body in motion. You're traveling at the same motion the car is. Okay, so when that car suddenly stops, you're a second body within the car, and your body wants to continue in motion. Okay, even though the car has suddenly stopped. Okay, so what happens? What's going to exert? The seatbelt is going to exert a net. Okay, the seatbelt is going to exert a force on you to stop you. Okay, moving forward. Okay, so what is this an example of? Well, I think it's a really good example of inertia. You know, you want to keep moving until a net force acts upon them. Okay, so that, in my mind, that's a really good example of inertia. Okay. Okay. Also, I mean, you could argue that there's even some elements of the second law in that too, or even the third law. Okay, but that's what I'm going to pick. Okay, the larger car takes more force to move. Okay, so this is kind of a vague one that I'm not knocked out about, but I'm going to assume the larger car has more mass. Okay, and mass, more massive things have more inertia. Okay, so if it's at rest, okay, and you want to move it, it's going to take more force to get that to move, because it has a lot of inertia because of its large mass. Okay, so I think one example there that could be used is that you could use number 1. Okay, now there's another one too, and that's that a larger car takes more force to move. If you say moving is acceleration, okay, if that's accelerating, well then a large car, a more massive car, will take a larger force to accelerate because of its large mass. So in some ways, this is also a Newton's second law problem too, okay? If you assume the larger car is more massive and you assume it takes more force to move, that's acceleration, then you could argue it's also the second law. Okay, the third one, a person leans on a wall. Okay, you lean on a wall. You apply a force to the wall. Okay, you apply a force to the wall. Okay, and the wall pushes back. Well, the wall's not moving, and you're not moving, so you're all in equilibrium, right? The wall's in equilibrium, so you are in equilibrium. So when you push on the wall pushes back, you're in equilibrium. Okay, so what's happening here is this is for every action force, you pushing on the wall, there is a reaction force of the wall pushing back on you. So this is a pretty good example of action-reaction forces. Okay, last one. A brick sits on a table until you push on it. Well, this is, in my mind, another one of these 1 and 2 things, right? If it sits on a table, it's at rest. Okay, and until a net force acts on it, it doesn't want to move. So that's kind of an example in my mind that objects want to stay at rest if they're at rest unless a net force acts on them. So number 1 might be a good example for number 1. Now a second one might be, say, okay, a brick sits on the table and that's a mass, right? And you push on it, well, you're exerting force on it. Okay? And so then it begins to accelerate. Okay? And if a brick sits on a table until you push it, and when you push it, it accelerates, then that'd be a good example of the second law. Okay? Okay, I know that's a little vague, Let's think about it a little bit and remember these definitions, okay?